Impedance transformer. What do you do when your S parameters look terrible? If your source is 50 ohm and your antenna is 100 ohm, a significant portion of your power will just bounce off the antenna and travel back to the source. To fix this, we have to trick the microwave source. We need to insert a device between the source and the load that magically makes that 100 ohm antenna look exactly like 50 ohm. That is the job of an impedance transformer. The most elegant and widely used version of this in microwave engineering is the quarter-wave transformer. Let's break down the physical background, simplify the math, and walk through two real-world examples.
The background: fighting reflections with reflections. Before we look at the formula, it helps to understand the physical magic of why this works. Imagine sending a microwave signal down a line. If you place a very specific deliberate speed bump, a different impedance transmission line, right before the mismatched load, the wave will split. Part of the wave bounces off the front of the speed bump. The rest travels through, hits the mismatched load, and bounces back. If we make that speed bump exactly 1/4 of a wavelength long, something incredible happens. The wave that travels through the bump and bounces off the load has to travel a 1/4 wavelength forward and a 1/4 wavelength backward. That is a total extra distance of a half wavelength. A half wavelength delay means the wave's phase is shifted exactly 180 degrees. The two reflected waves are now perfectly out of phase. They collide, completely cancel each other out through destructive interference, and 100% of the energy is forced to transfer into the load.
Deriving the formula. To figure out exactly what impedance that speed bump needs to be, we start with the master equation for microwave transmission lines, the input impedance equation. It calculates exactly what impedance a wave feels when looking down a length of line, L, terminated by a load, ZL. The formula is shown here. This looks intimidating, but because our transformer is exactly a 1/4 wavelength long, the math completely collapses. The term beta L calculates the phase shift. For a 1/4 wavelength, beta L is exactly 90 degrees, or pi/2 radians. The tangent of 90 degrees approaches infinity. Because the tan terms become infinitely large, the non-tangent terms, ZL and Z0, become practically zero in comparison and drop out of the equation. The tangents cancel each other out, and the formula simplifies to a beautiful, clean equation shown here. Note, I am using Z1 here to represent the characteristic impedance of our new 1/4 wave transformer section. We want our system to be perfectly matched to our source impedance, Z0. So we set Zin equals Z0 and solve for the impedance of our transformer section, Z1 equals square root of Z0 times ZL. This is the golden rule of the 1/4 wave transformer. The impedance of the matching section must be the geometric mean of the source and the load. Example 1. The pure resistive load. Let's say you are designing a radar system. Your main microstrip feed line is a standard 50 ohm. Z0 equals 50. You want to attach a patch antenna that has an impedance of 100 ohm. ZL equals 100. Because both values are purely real, resistive, no imaginary or reactive parts, this is a straightforward calculation. Calculate the transformer impedance. Z1 equals square root of 50 times 100 equals square root of 5,000 equals approximately 70.7 ohm. The physical design. You need to insert a piece of transmission line that has a characteristic impedance of 70.7 ohm. In microstrip design, higher impedance means a narrower trace. So you will route your normal 50 ohm trace, then narrow it down significantly for exactly 1/4 wavelength, and then attach it to the antenna. Example 2. The complex load, the two-step dance. Real-world loads are rarely perfectly resistive. What if your antenna has some parasitic inductance, giving it a complex impedance? Source, Z0 equals 50 ohm. Load, ZL equals 50 plus J 50 ohm. If you try to plug this into our simple formula, the result is a complex number. You cannot manufacture a transmission line with a naturally complex characteristic impedance. It would require building infinite continuous resistors right into the copper trace. We have to solve this in 2 steps, using a transmission line trick. Step 1. Rotate to the real axis. If you connect a standard 50 ohm transmission line to your complex load, the wave traveling along that line will experience a changing impedance. As you move further away from the load, the inductive, positive J, and capacitive, negative J, effects cycle up and down. If you make this line the exact right length, the imaginary part of the impedance will hit zero. The impedance becomes purely real. Using microwave network calculations or tracing a circle on a Smith chart, a load of 50 plus J50 creates a voltage standing wave ratio, or VSWR, of about 2.62. If we extend our line until we hit the maximum real impedance point, our new rotated load becomes Z real is about 131 ohm. Step 2. Apply the quarter wave transformer. Now we have a purely real load of 131 ohm. We just use our golden rule formula from example 1. Z1 equals square root of 50 times 131 equals approximately 80.9 ohm. The final physical layout. Starting from your 50 ohm source, you would first lay down an 80.9 ohm trace that is exactly a quarter wavelength long. Then you would lay down a standard 50 ohm trace for a specific distance to cancel out the positive J50 reactance, and finally attach your complex load. Enjoying this? Smash that like button and subscribe for more RF and microwave engineering content. Drop a comment below with what you want to see next. I'm reading every single one. Let's get back to it. Thank you.